Hey, welcome to the Explainer. Today we're going to break down a really tricky but super powerful coding problem that's all about finding almost duplicates in a smart, efficient way.
All right, let's just jump right in. Imagine this. You got this massive data set, right? We're talking thousands, maybe even hundreds of thousands of numbers. And your job is to find a pair of numbers that are not only close in value, but are also physically close to each other in the list. How would you even begin to do that without taking forever?
So the official name for this puzzle is Contains Duplicate 3. Yeah, I know, it's a bit of a mouthful. But really, it all comes down to a very specific set of rules we have to follow to find what we're looking for.
Okay, so here's the deal. There are 3 rules, and we need to find just one pair of numbers that satisfies all 3 at the same time. Rule 1, they can't be the same element, so their positions I and j must be different. Rule 2, they have to be close to each other in the list. The distance between their positions can't be more than some limit we call index diff. And rule 3, their values have to be close. The difference between the numbers themselves can't be more than another limit, value diff. Okay, let's make this real with an example. We've got the list 1, 2, 3, 1. Our index diff is 3 and our value diff is 0. So we spot those two ones. The first one is at index 0 and the second is at index 3. Let's check the rules. How far apart are their positions? 3 minus 0 is 3. Is that less than or equal to our index diff of 3? Yes. Okay, how far apart are their values? 1 minus 1 is 0. Is that within our value diff of 0? Yes again. We got a match, so we can just stop and return true.
But here's the kicker. That was easy with 4 numbers. What if you have 100,000? Just checking every single pair against every other one? No way. That would mean billions of checks. It's just way, way too slow. Your computer would not be happy. We need a better plan. So how in the world do we solve this thing efficiently? Well, let's start by tackling that first constraint, the one about position. And for that, we're going to use a really clever technique called a sliding window. Think of it like this. It's a magnifying glass, but it has a fixed size. The size of our magnifying glass is going to be exactly index diff, and we just slide that magnifying glass across our entire list of numbers one step at a time. And this is a huge deal, because by only ever looking at the numbers inside our little window, we've already solved half the problem. Any pair we find inside the window is guaranteed to be close enough position-wise. We've automatically taken care of that index diff rule. Pretty neat, right? Okay, so we've got the position part handled. But what about the values? How do we efficiently check for value differences inside that window? Because just checking every number against every other number, even inside a small window, still isn't fast enough. We need another trick up our sleeve. This is where our secret weapon comes into play. We need a special kind of tool, a data structure that can tell us almost instantly if a number we're looking for exists within a certain range. And that tool is called an ordered set. And its superpower is exactly what it sounds like. It keeps everything inside it perfectly sorted all the time. No matter what we add, no matter what we take out as our window slides along, the set keeps everything in order. It's going to do all the heavy lifting for us. And just look at the difference this makes. With a regular unordered list, finding a number is like trying to find a word in a book with no index. You have to scan every single page. It's slow. But an ordered set, that's like having a perfect index. You can jump right to where you need to be. It's just ridiculously fast in comparison. Okay, so let's put it all together. Let's combine our sliding window with our super fast ordered set and actually walk through that example step by step. This is where the magic happens. All right, same example as before. Index diff is 3, value diff is 0. We're going to go through this one number at a time, using our ordered set to keep track of what's currently inside our sliding window. First up, the number 1. Our ordered set is totally empty, so there's really nothing to check against. We just pop the 1 into the set. Easy enough. Okay, next up is the number 2. Now we ask our ordered set a question. Since our value diff is 0, we're asking, hey set, do you have any numbers between 2 and 2? In other words, do you have a 2? The set says nope, so we add 2 to our set. Now it's holding on to 1, 2, perfectly sorted. And we do the exact same thing for the number 3. We ask the set, got a 3 in there? Nope. Okay, in it goes. Our set now contains 1, 2, 3, still perfectly sorted. And here it is, the moment of truth. We get to the last number, which is a 1. We ask our set the same question again, is there a number in here between 1 and 1? And this time, because our set is so smart and so fast, it immediately says, yes, I've got a 1 right here. And bam, that's it. We found a pair that meets both our rules. We can stop right there and return true. Game over. So you might be thinking, wow, that was a lot of work with windows and sets. But why did we do it? It all comes down to one thing: insane speed. The performance boost we get is just staggering. You know, the simple way, just checking every number against every other number, we call that O of n squared in computer science. All you need to know is that as your list gets bigger, the time it takes just explodes. It gets out of control really, really fast. But our solution, with the sliding window and the ordered set, it's way, way faster. Its time complexity is O of n log k. Now, the n is still the size of our list, but that k, that's just the tiny size of our window, and that makes all the difference in the world. Let's put some real numbers on this. For a list with 100,000 items, that brute force method would take roughly 10 billion operations. 10 billion. Our smart algorithm, less than 2 million. I mean, that's the difference between your program crashing or timing out and it finishing in the blink of an eye.
So, to wrap it all up, what did we really do here? We took one big, complicated problem and we broke it into two smaller, easier ones. The sliding window, that took care of the position constraint. The ordered set, that took care of the value constraint. We used the right tool for the right job, and that's what created this super efficient solution.
And here's the thing. This pattern, this idea, it's not just for this one specific puzzle. Think about it. Analyzing stock market data in real time, looking for strange patterns in sensor data from a machine, it's the same core idea. So the question I want to leave you with is, now that you know this trick, what other hidden patterns could a sorted